Hello, Math Studies students. In this lesson, we are going to discuss mutually exclusive events. We'll define what that is, but the main part of the lesson is we're going to talk about using probability laws. And the main goal of this, we'll know we're successful if we can identify which probability law we need to use. So identifying the correct probability law. I'm less worried about the actual math that you need to use than just knowing what formula to use. So to start with a very brief definition here on mutually exclusive events. Mutually exclusive events are events that cannot happen at the same time. Cannot happen at the same time. Examples of this would include like being in a room. What's the probability I'm in room 309 and 308 at the same time? Yeah, it's 0. It cannot happen. I cannot be in the same place at the same time, two different places at the same time. Another case would be like, what's the probability of rolling heads and tails on one coin? Well, I could roll heads, I could roll tails, but I could not do those two things at the same exact time. So they are what we would call mutually exclusive events. Anything that cannot happen at the same time. Now I've got a slide here filled with formulas. These are all the different probability formulas and laws that we've either covered or are now introducing here today. The older ones are towards the bottom. You'll notice it's 4 bullet points. There's 4 different formulas, and all of these are in your formula packet. I've tried to write them very similar to how they appear in your formula packet, but I would still look at your formula packet, make sure you know where these formulas are, make sure that they're at least similar enough or you understand the differences of how I've written them and how they are in your formula packet. The first one, sometimes referred to as the addition law of probability. I think our formula packet calls it combined events. And I've written it 2 different ways here. I've written it once just straight as a formula here, which says the probability of A union B, or A or B, is equal to the probability of A plus the probability of B minus the probability of A and B, or A intersect B. And then below that, I just wrote that in words, you know. So again, that upside down U looking thing means either or. And I'm sorry, the regular U looking thing is either or, and then the upside down one, the one that sort of looks like an and, stands for both A and B. When can we use this? Well, it's nice because it's got a lot of stuff in it. It's got or, it's got and, it's got the individual probabilities. But you'll notice overall there are, if I circle this one as well, there's 4 different probabilities in this formula. And in order to use this, you need to know at least 3 out of those 4 probabilities. So you'll look below us and we'll see that a lot of the other formulas, like the one right below it, only has 3 different parts. The one below that, again, has an and then one part there, and then the conditional part, so 3 different parts, and at the very bottom, 3 parts, 1, 2, 3, 3 different probabilities. This first one, the combined events, is the only one that has 4 parts. So it's great because it's got all the parts in it, but you can only use it if you know 3 out of 4 of those parts. So if you only know 2 different probabilities, you can't use the combined events formula. You got to have at least 3 of those 4 probabilities. Must know 3 things. Now we get down to the mutually exclusive events formula. It's called the mutually exclusive events formula. And when can you use it? When they tell you that you have mutually exclusive events. If you don't have mutually exclusive events, you can't use this formula. So it's in the title. Use this whenever you see the word mutually exclusive events, and if you don't see that word, do not use this formula. You'll notice that this formula is very similar to the one above it, the combined events formula. It still has the probability of A or B. It still has the probability of A. It still has the probability of B being added on. The only thing that's missing is the part that I circled above in green, which is the probability of A and B. Why is that not included in this formula? Well, the probability of A and B would be 0 if they're mutually exclusive, because mutually exclusive means A and B cannot happen at the same time. So what's the probability of them both happening at the same time? It's 0. So they just took that part out of the formula, and so it's just a little bit simpler. Honestly, I don't even think this formula is necessary, because as long as you know mutually exclusive has the probability of A and B equaling 0, you could just use the first one. But it is in your formula packet, and again, you can only use it when it says mutually exclusive. Now we get down to conditional probability. Our last video talked about this. We used this formula whenever we had a tree diagram with conditional probability. You usually do not need it for a Venn diagram or for tables, though it would work. Really, anytime you see that word given is when we're going to use this one. Or a similar word like knowing that or something like that that lets us know there's additional information. Just a reminder that that line right there reads given. So this reads the probability of A given B is equal to the probability of A and B divided by the probability of B. And last but not least, independent events. We learned this formula a while back. If two events are independent and we want to know the probability of both of them happening, A and B happening, we take the probability of A times the probability of B. And we also said that we can extend that. Usually when you deal with these formulas, they'll tell you if they're independent or not. So if they're independent events, it'll say independent, and then you should use this formula. If they're mutually exclusive, it'll tell you, and then you should use the mutually exclusive formula. If it says given, you should use the conditional probability, and if you have at least 3 different probabilities that work in this formula, you can use the combined events formula. So let's try it out here with a couple examples. First and foremost, we have probability of A equals 1/2, probability of B equals 1/3, probability of A or B, we don't know, it's little p. And the directions say find little p. And little p is the same thing as A or B. So that's what we're going to find. First and foremost, it says A and B are mutually exclusive. Well, we have a formula called mutually exclusive, so let's write that down. First step, write down the formula. A or B is equal to the probability of A plus the probability of B. Now let's start filling things. Oh, I'm sorry. Yeah, that's mutually exclusive. Had a little brain freeze there for a second. Probability of A, we know, is 1/2. Probability of B, we know from, again, up above here, it is 1/3. Put our plus sign and our equal in. Now the probability of A or B. Well, they told us that as well. It's little p. And what was the problem asking? It was asking for us to find little p. So let's combine like terms here, or combine these fractions. Notice the denominators are not the same. In order to add fractions, you need to have a common denominator. What does both 2 and 3 go into? That would be 6. How many times does 2 go into 6? 3 times. So we multiply the top and the bottom of this fraction here by a 3. So 3 times 1 and 3 times 2, which gives me 3 over 6. And then if I look at the next one here, I've got the 1 over the 3. 3 goes into 6 2 times, so I'd multiply the top and the bottom by 2, and I get 2 over 6. And when I combine those, I have 3 6 plus 2 more 6, which gives me a grand total of 5 6. Sorry, I ran out of room and had to put that on the side. So little p, which is what we were trying to find in this problem, find little p, is 5 6. Okay, that's if we know that A and B are mutually exclusive events. Now, what happens if they're not? What if they are, for example, independent events? Well, that changes everything, because now we can't use the mutually exclusive formula. So A and B are independent events, but I remember having an independent events formula. It says the probability of A and B this time, be very careful whether it says and or, is equal to the probability of A times the probability of B. So let's start filling in some numbers here. We know that B was 1/3, working backwards. We know that A was 1/2. We're going to multiply those two things together, and they should equal the probability of A and B. Now be careful. A and B was not actually what we were looking for. We were looking for A or B, also known as little p. But this is the only formula we can use, so we're starting with this, and it'll lead us somewhere else. So the probability of A and B is 1/2 times 1/3. Multiplying fractions are easy. We go straight across, and we get 1/6 as that probability. But again, we haven't answered the question, because the question said, find little p. And we have not found little p. We found the probability of A and B. But we sit and ask ourselves now, we were told originally that probability of A was 1/2. B was 1/3, and now we know that the probability of A and B is 1/6. So how many different things do we know? We know 3 different probabilities. A, B, A, and B. All 3 of those. So which formula can you use when you have 3 things that we know? The combined events formula. I'm going to write that down, which says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. We can throw all these numbers in now. We know that the probability of A was 1/2. We know that the probability of B was 1/3. We know the probability of A and B was what we just figured out, 1/6. And we're looking for the probability of A or B, also known as little p. When we combine these, 1/2 plus 1/3 we did earlier, and we know that's 5/6. And then if I subtract 1/6, that will be equal to 4/6, or 2/3. And that would be the value of little p if A and B are independent. Two other little problems here. We'll do at least one of them together. It says if the probability of Q is 0.5, probability of R is 0.3, and we know the probability of Q or R is 0.75, are they independent? Are they independent? Well, I see independent, which makes me want to say I should use my independent formula. Now, it's not saying that they are independent. They're saying, are they independent? Well, I'm going to assume they are. I'm going to pretend they are. And the independent formula says the probability of A times the probability of B is equal to the probability of A and B. So I would take my 0.5, I should probably rewrite this. Again, the A is going to be like the Q, and the B is going to be like the R. And so, actually, let me clean that up. So we'll have Q here, we'll have R there, and this will be Q and R. So let's fill some things in. We've got 0.5 times 0.3, and that would be equal to 0.08. Nope, let's try one more time. I added 0.15. So 15% is probability of Q and R. But that's if they're independent, because I used the independent formula without knowing they were independent. Now what I'm going to do is I'm going to check it. And I'm going to check it using the combined events formula. The reason I'm going to use the combined events formula is because they gave me three things. 1, 2, 3. So the combined events formula says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And again, we've got Q's and R's, but I'll just make a direct substitution there. So we know that Q or R is 0.75, so I'll put that with the or. We know that A, which I'm calling Q here, is 0.5, and I know that B, which we called R earlier, was 0.3, and this was the one part I didn't know, but we sort of figured out what we think it might be. If they're independent, that's 0.15, so I'll write that in here. Now all I have to check is, are these things actually equal? If they're equal, then this answer must be right, so they must be independent. If they're not equal, then that answer was wrong, and they're not independent. So let's add up the right side. We have 0.5 plus 0.3, which gives me 0.8, so I'll have 0.75 equals 0.8 minus 0.15. Well, 80% minus 15% gives me 65%. So 0.8 minus 0.15 gives me 0.75. And that is not equal to 0.75. So are they independent? No, they are not independent. Because once again, we tried using the independent formula. If they were independent, this would be our answer of the probability of Q and R. But then when we checked it in the combined events formula, we didn't get a true statement. So that answer must have been wrong, which means they are not independent. If you think you got that one, why don't you pause the video and try to do part B on your own. All right, to check this, we can do a similar process here. Again, if they were independent, we could use our independent events formula, which says that taking two things and multiplying together will give their and. So the probability of B times the probability of C should equal the probability of B and C if they're independent. So let's plug these in. I have 0.6 times 0.3. Notice I don't write the P's when I'm plugging in the numbers. P stands for probability, and the probability of B is 0.6. Don't write P 0.6. That doesn't actually mean anything in this problem. So we have 0.6 times 0.3, which gives me an answer of 0.18. I think I did my math correctly that time. And so that's the probability of B and C both occurring. That's if they're independent, and we're trying to figure out, are they? So we'll check our answer in the combined events formula, which says the probability of B or C is equal to the probability of B plus the probability of C minus the probability of B and C. We'll fill in everything we know. 0.72 they gave us for the OR. Probability of B is 0.6, probability of C is 0.3, and we're subtracting the answer we just got, which is 0.18. 0.6 and 0.3 add up to become 0.9, bringing everything down, minus 0.18. 0.9 minus 0.18 is 0.72. 0.72 is equal to itself, so that's a true statement, which means this answer was correct, and the formula I used to get that answer was the independent events formula. So are these independent events? Yes. Yes, they are. If any of these examples were confusing, all I can say is you got to take a look at this homework here. Page 290 and page 294, students find the content in this material to be more challenging than others. Why? Because we have those 4 formulas, and you need to take careful note of which formula to use based on what they've described in the problem. And then you need to practice, because there's algebra involved, there's substitution, and a little bit of thinking. So please take a look at the problems on page 290 and 294, and we will see you next time.